Welcome back. This is Volume 2 of Simplicial lattice field theory. Volume 1 gave us spacetime, the Lorentzian signature, 3 Fermion generations, and the speed of light, all from the geometry of the 24 cell. But a vacuum alone contains no particles. For stable particles to exist, they need topological protection. That's what this paper is about. We compute the homology of the 24 cell and extract 3 major results: baryon number conservation, color confinement, and charge quantization, all from integer-valued boundary operators, with no free parameters. Quick recap. The D4 lattice has a unit cell, the 24 cell, with 24 vertices, 96 edges, 96 faces, and 24 cells. Volume 1 showed that topological frustration forces the lattice to break O4 symmetry, giving us Lorentzian spacetime and 3 Fermion generations. Now we go deeper. The 24 cell is not just a geometric object, it's a simplicial complex with a boundary structure, chain groups, and homology. Those homology groups are the physical content of this paper. In standard quantum field theory, conservation laws follow from Noether's theorem: continuous symmetry gives conserved current. In SLFT they're stronger, topological. A charge is a homology class. No local deformation can change it. Why topology? Because a stable particle must be a configuration that cannot be continuously deformed to nothing. The integer that counts how many times it wraps around a non-contractible cycle is the winding number, and it cannot change under any smooth deformation. The key fact: the boundary of the 24 cell is homeomorphic to the 3 sphere. The topology is exactly that of S3. Every cycle on this complex either bounds a surface, or it doesn't. Those that don't are topologically protected. Those are the particles. The 24 cell gives 4 chain groups, C0 through C3, 1 for each dimension of simplex. The boundary operators map each group to the one below, recording which faces bound which cells, with orientation signs. The critical identity, boundary of a boundary, is 0. Delta k-1 composed with delta k equals 0. This makes homology well defined. All 3 boundary matrices are integer valued. Their ranks are computed by singular value decomposition to machine precision exact, not approximate. The 3 ranks are 23, 73, and 23. Rank of delta 1 is 23, the 24 by 96 matrix connecting vertices to edges, with rank v-b0 equals 24 minus 1 equals 23. Rank of delta 2 is 73, this saturates the upper bound forced by delta 1 composed with delta 2 equals 0. The kernel of delta 1 has dimensions 73, and rank of delta 2 achieves that maximum. Rank of delta 3 is 23, by Poincaré duality on S3, rank of delta k equals rank of delta 3 minus k. So rank of delta 3 equals rank of delta 1. Not a coincidence, a consequence of the 24 cell self-duality. From the ranks, the Betti numbers follow immediately. B0 equals 1, the vacuum is connected. B1 equals 0, kernel and image both have dimension 73, so H1 is trivial. B2 equals 0. B3 equals 1, the fundamental class of S3. These are exactly the Betti numbers of the 3 sphere. The 24 cell boundary triangulates S3. 2 numbers carry all the physical weight. B1 equals 0 gives us color confinement, and B3 equals 1 gives us baryon stability. Everything else follows from there. The central structural result. The 96-dimensional face space splits into 3 orthogonal subspaces. 73 coexact modes, the image of the transpose of delta 2, are the propagating degrees of freedom of the lattice gauge field. 23 exact modes, the image of delta 3, are topologically frozen. They carry non-perturbative information but cannot propagate. 0 harmonic modes, because B2 equals 0. 73 plus 23 equals 96 equals F. This is the master decomposition. Every coupling constant, every mass ratio, every gravitational entropy coefficient in the theory derives from this single splitting of the face space. B3 equals 1 means H3 is isomorphic to the integers. The generator is the fundamental class, the 3 chains summing all 24 oriented octahedral cells. A baryon is a 3-chain with zero boundary and non-zero class. Its winding number W is the integer coefficient. Because H3 is discrete, W cannot change under any continuous deformation. Baryon number is absolutely conserved. Proton decay into a positron and neutral pion would require delta W equals -1. That's topologically forbidden. The proton is stable not from fine-tuned couplings, but from the discrete topology of the lattice. B1 equals 0 gives us confinement. The A2 subalgebra of the D4 root system defines 3 color directions. To propagate an isolated color charge from one vertex to another, you create an oriented edge path carrying color flux. Close that path into a loop. Since B1 equals 0, every closed loop bounds a phase chain, and the gauge energy stored is proportional to the area, which scales with path length. Energy equals tau string times L. Isolated color charges cost infinite energy at infinite separation. Only color singlet combinations, where the total A2 weight vanishes, avoid the flux tube. Those are baryons and mesons. Charge quantization follows from 2 facts together. First, H0 and H3 are both isomorphic to the integers, discrete groups. Any conserved charge associated with these classes takes integer values. Second, the A2 color structure forces quark charges into thirds. The smallest gauge invariant combination is 1/3 of the fundamental charge. The result, Q equals n over 3, for integer n, charges 0, plus minus 1/3, 2/3, 1, not imposed by hand, but derived from the topology of the 24 cell and the A2 substructure of its root system. Every result in paper 2 traces to one row of this table. B0 equals 1, connected vacuum. B1 equals 0, color confinement. B3 equals 1, baryon conservation. 73 coexact modes, propagating gauge field. 23 exact modes, topologically frozen. And one more, 23 plus 1 divided by 96 equals 1/4. This is the Beakenstein-Hawking coefficient, the ratio of black hole entropy to horizon area, emerging here from pure combinatorics, before gravity even enters the picture. Charge is not a continuous field property. It is discrete homology, determined by the integer boundary operators of the 24 cell. Thank you for watching. Volume 2 has given us the topological skeleton of particle physics, quantized charge, color confinement, stable protons, from the homology of a single polytope. Volume 3 derives particle masses from the mass-volume principle and the spectral geometry of the D4 lattice. Full papers series on ZENODO link on screen. See you in Volume 3.